Howdy folks, I've been asked to work this MyMathLab question from our textbook, and in this problem we're told that we have a flower garden sitting inside of a larger lawn, and our goal is to minimize the area of the combined area, so that's that net area here, that net rectangle. Our goal is to minimize that. However, we need to have a garden that has an area of 154 square meters. And we want to have, I guess, maybe a walkway or something like that around this flower garden. So we don't want to make too big of a space. We want to minimize the total space. But here, kind of interesting question, usually our constraint is something to do with length or something like this. We're constrained by the fact that although we want as small of a rectangle as possible, we're constrained by the fact that we must have a flower garden with 154 square meters. And we've got to have this pathway around it. So let's go ahead and give it a shot. Our goal is to minimize the total area. So the total area here would be what? Well, let's go ahead and apply some variables to this. I'm going to go ahead and call this h, and we'll go ahead and call this dimension here width, because we can adjust those. I could have used maybe, I could have called this h, and I could have called this w, and then I would have come up with a different area function, and everything would still work out okay. So there's nothing that says you have to pick this as your h and w, but the numbers work out a little bit, we're able to get through the problem a little bit zippier if we do it this way. So then what is our area function? Well, our area function would be 4 plus w times 2 plus h is how we'd compute the area of this large rectangle here. Let's make sure that makes sense, folks. So if we want to compute the area of that large rectangle, its width is going to be this 2 plus this w plus this 2. And the height is going to be this expression, right? The height is going to be, sorry, that's not quite right. The height is going to be this 1 plus this h plus this 1. So if we think of the total height, that's how we got 2 plus h for the total height. And for the total width, we had this 2 plus this w plus this 2, which is why I gave 4 plus w for the width. Okay. I could do it now, I could do it later. Before I FOIL that out, let's go ahead and look at our constraint. We're constrained by the fact that the area of the garden must equal 154 meters squared. Well, the area of the garden is simply the height times the width. That's how we get the area of the garden. And if I solve this for the variable I want to eliminate, and to be able to answer the MyMathLab questions the way they want, I'll go ahead and solve the constraint for w. We get that the width is equal to 154 divided by the height. So now if I plug all of this into my area function, that's the function I want to optimize, we get the area in terms of the function h is equal to 4 plus 154 over h. So I replace the w here with the expression for w times the 2 plus h factor, and then we'll just go ahead and FOIL this out. If I FOIL this out, I get 8 plus 4h plus 308 over h plus 154. So I went ahead and FOILed that out, double check. Notice that when I multiplied this h to this 154 over h, for those two factors, the h is canceled. And if we clean this up just a little bit more, we get that the area as a function of h is equal to 162 plus 4h plus 308 over h. Now we're ready. Now we've got a function that we want to optimize. So we take the derivative of this function and we get 4 minus 308 over h squared, and let's find the critical numbers. So the critical numbers of a are where a prime is equal to 0, or a prime of h is undefined. But of course, a prime of h being a nice, well, it's not defined at 0, but the domain that we're going to use, so I guess we should say this, the domain that we're going to use, the domain of a, is going to go from 0 to infinity, and that should make sense. We only want to plug in h value, positive h values. By the way, you could argue that maybe there's something different to use for that right endpoint for the domain. It doesn't really matter. It's going to be an open interval. So if you make a different argument, I could certainly buy that. But we'll go ahead and use 0 to infinity here. So this can't happen because on the interval from 0 to infinity, we're always defined. And so then simply we only get critical numbers from where the first derivative is 0. So that happens when 4 minus 308 for h squared equals 0. Or adding 308 over to the other side, we get 4 is equal to 308 over h squared. Or 4h squared equals 308, or h squared, let's see, I think that's 77. So we get h is equal to plus or minus the square root of 77, but of course we're only going to take h equals the square root of 77, that positive entry, because of our domain here. Okay, so we now have the dimension of the height that will maximize our area, and let's go ahead and find, so h we just said was the square root of 77, and w then would be 154 divided by the square root of 77 at this particular critical number. But what we haven't yet done, in fact I misspoke a second ago, what we haven't yet done is found that we've actually found the minimum values for the total area. So what we need to do is we need to check that. Let's take the second derivative. I prefer to use the second derivative test on this. So taking the second derivative of our function, the second derivative of h, let's see, I'm looking at this function here, would be a positive 616 over h cubed. Double check me on that, but I think I'm okay. And anyway, if we were to plug in our square root of 77, that critical number, into the second derivative, we would get something. I don't really care what we get. We would get a number that is positive. Why is that important? Well, by the second derivative test, h equals the square root of 77 is the location of a local minimum. Why a local minimum? Because we've already said that this was, well, we just said that this was concave up on the interval, and so that's what we get from this bit of information right here. And the fact that it was a place where the first derivative was 0, we got that from this information right here, says that we've got a horizontal tangent line on a point on a concave up interval. The only place that happens is as a local minimum. That's our second derivative test. Now, since h equals the square root of 77 is the only local extrema on 0 to infinity, it's also the corresponding global extrema. What I've just stated there is that useful theorem, which we saw in our section 4.5 notes. Okay? So remember that the second derivative test only tells us that we've actually found a local minimum. But this useful theorem says if we only have one local extrema on an interval, then it must be its corresponding global extrema. So h equals the square root of 77 is the global min of a on the intervals on the interval from 0 to infinity. So the dimensions, and so our final answer then, the dimensions that will maximize, or excuse me, minimize our area are the square root of 77 feet for the height by 154 over the square root of 77 for the so this was our, we do have to be a little bit careful here. This is what we've labeled as height, and this is what we labeled as width. And there we have our answer. Folks, I hope this was helpful. If you have any questions, please let me know.